The phenomenon of grokking, where a model's test accuracy suddenly improves long after achieving 100% training accuracy, has been observed in neural networks trained on modular arithmetic tasks. Contrary to the prevailing view, this work demonstrates that grokking is not exclusive to neural networks or gradient descent-based optimization. Instead, it can also occur when learning modular arithmetic with recursive feature machines, RFM, an iterative algorithm that leverages the average gradient outer product, AGOP, to enable task-specific feature learning with general machine learning models. When RFM is used in conjunction with kernel machines, it yields a rapid transition from random, near-zero test accuracy to perfect test accuracy. Notably, this transition cannot be predicted from the training loss, which remains identically zero, or from the test loss, which remains constant in initial iterations. Rather, it is entirely determined by feature learning, where RFM gradually learns block-circulant features to solve modular arithmetic. Parallel findings are observed in neural networks that solve modular arithmetic, where they also learn block-circulant features. Theoretical evidence suggests that RFM utilizes these block-circulant features to implement the Fourier Multiplication Algorithm, previously posited as the generalizing solution learned by neural networks on these tasks. These results demonstrate that emergence can arise purely from learning task-relevant features and is not specific to neural architectures or gradient descent-based optimization methods. Moreover, this work provides further evidence for AGOP as a key mechanism for feature learning in neural networks, highlighting the importance of task-specific feature learning in achieving sudden improvements in test accuracy. Accuracy and the rapid emergence of skills in modular arithmetic tasks have garnered significant attention recently. Some studies suggest that this rapid emergence might be an illusion due to the mismatch between discontinuous evaluation metrics and continuous training loss. The authors propose that instead of accuracy, test or validation loss, or training loss could be a more suitable measure of progress. They argue that skills may emerge once the training loss falls below a certain threshold in the optimization process, aligning with classical generalization theory. This work focuses on the emergence of skills in modular arithmetic, demonstrating that sharp emergence arises from feature learning, independent of other modeling and training aspects, and is not predicted by standard measures of progress. The authors clarify the nature of feature learning leading to skill emergence in modular arithmetic. The key contributions of this work are threefold. Firstly, grokking modular arithmetic is shown to be not specific to neural networks. Secondly, it is demonstrated to be not tied to gradient-based optimization methods. Lastly, it is proven to be not predicted by training or test loss or accuracy. The authors achieve this by showing grokking for recursive feature machines, an algorithm that enables task-specific feature learning through iterative use of the average gradient outer product. Researchers have developed a novel method to enable feature learning in kernel machines, which lack native feature learning capabilities. This approach, known as RFM, involves training a kernel machine, computing the AGOP matrix to extract task-relevant features, and transforming input data using these learned features. A representative example, illustrated in Figure 1, demonstrates RFM's ability to learn modular addition without gradient-based optimization, achieving perfect training loss and 100% test accuracy. Notably, the AGOP feature matrices exhibit a striking gradual emergence of structure, despite constant training loss. To track the evolution of feature matrices toward a structure conducive to modular arithmetic, two hidden progress measures are introduced. These measures reveal a gradual, nearly linear, progress toward a generalizing model. Theoretical evidence supports the finding that the learned circulant features result in kernel machines implementing the Fourier Multiplication Algorithm for modular arithmetic. This research suggests that kernel RFM and neural networks, despite using different predictive models, discover similar algorithms for implementing modular arithmetic, implying similar out-of-domain generalization properties. The emergent properties of machine learning models arise from their ability to learn features, making understanding these properties crucial. The paper is structured to introduce necessary concepts and definitions, demonstrate emergence with random feature machines, RFMs, and neural networks, and prove that kernel machines learn the Fourier matrix with circulant features. The authors introduce learning modular arithmetic, where models learn modular functions f** operator, a, b, equals g, a, b, mod p, mapping from zp times zp to zp. To train models on modular arithmetic tasks, input label pairs are constructed using one-hot encoding of input and label integers. Key concepts for theoretical analysis are defined, including the complex inner product and discrete Fourier transform, DFT. The complex inner product, a map from CD times CD to C, is the conjugate transpose of one vector multiplied by another. The DFT, a unitary matrix mapping from CD to CD, is the matrix product of a vector with a unitary matrix F. Circulant matrices, crucial for understanding features learned by RFMs and neural networks in solving modular arithmetic tasks, are defined as matrices containing blocks of circulant matrices. A circulant matrix has rows that are cyclic permutations of each other, representable as a cyclic permutation of a vector. This concept is essential for understanding the emergent properties of machine learning models in modular arithmetic tasks. The Recursive Feature Machine, RFM, algorithm is presented, which takes in training data x and y, a base kernel k, number of iterations t, matrix power s, and bandwidth L. The algorithm iteratively solves for alpha and updates the feature matrix M using the kernel regression solution and the circulant matrix representation. A circulant matrix C is defined as a matrix where each row is shifted one element to the right of its preceding row, and a Hankel matrix is defined as a matrix with constant antidiagonals. The average gradient outer product, AGOP, matrix G is introduced, defined as the average of the outer product of the Jacobian of a predictor function f evaluated at different data points. The top eigenvectors of the AGOP matrix represent the most relevant input features that influence the output of a general predictor. AGOP has been previously used to improve sample efficiency of machine learning models, particularly in multi-index models where the target function depends on a low-rank subspace of the data. Recent studies have also shown that AGOP enables feature learning in general machine learning models and provides a mechanism for understanding feature learning in neural networks. Notably, while AGOP was initially motivated by multi-index examples, it can recover useful features for modular arithmetic that are not low-rank. The neural feature ansatz, which posits that AGOP is a mechanism through which neural networks learn features, is also mentioned. The AGOP is utilized to improve the sample efficiency of predictors trained on modular arithmetic, a concept that will be further explored in this paper. The Recursive Feature Machine, RFM, algorithm, when combined with kernel machines, offers a powerful tool for feature extraction. The neural feature alignment, NFA, hypothesis posits that neural networks learn features at each layer by leveraging the approximate group orthogonality property, AGOP. Notably, the AGOP can be computed for any differentiable predictor, including kernel machines lacking native feature learning mechanisms. The RFM algorithm iteratively applies the AGOP to extract features from given data samples, involving two primary steps: predictor training and AGOP update. In predictor training, the function f, t, x, is computed using the Mahalanobis kernel k, mount, with coefficients alpha derived from the inverse of the kernel matrix k, x, x, mt. Subsequently, the AGOP update step updates the matrix mount plus 1 using the matrix power of the AGOP, g, f, t, s, where s greater than 0. The authors demonstrate the efficacy of the RFM algorithm with the quadratic kernel on modular arithmetic with modulus p equals 61, trained for 30 iterations. Interestingly, test accuracy, test loss, mean squared error, over all output coordinates, and test loss of the correct class output coordinate remain unchanged for the first 8 iterations, followed by a sharp transition. Conversely, the circulant deviation and AGOP alignment display gradual progress towards generalizing solutions, despite the initial stagnation in accuracy and loss metrics. The NFA hypothesis offers critical insights into how neural networks learn features at each layer by utilizing the AGOP. This understanding can be applied to improve the design and training of neural networks, highlighting the significance of the RFM algorithm and its potential applications. The paper discusses the Gaussian kernel k, x, x, m, and its application in recursive feature machines, RFM. The Gaussian kernel is defined as express, parallel xx squared, m, where for z element of road, parallel z squared, m equals zmz, and L is the bandwidth. The authors demonstrate that RFM exhibits sharp transitions in performance on 4 modular arithmetic tasks: addition, subtraction, multiplication, and division due to the emergence of features, which are block-circulant matrices. They use a modulus of p equals 61 and train RFM with quadratic and Gaussian kernel machines. The top 2 rows of Figure 2a show that the first several iterations of RFM result in near zero test accuracy and approximately constant, large test loss. However, continuing to iterate RFM leads to a dramatic, sharp increase to 100% test accuracy and a corresponding decrease in the test loss later in the iteration process. The authors also observe that the test loss for the output coordinate, logit, corresponding to the correct class closely tracks the total test loss. This suggests that the near constancy of the total square loss over the first few iterations does not conceal steady improvements in the predictions of the correct class. In order to understand how RFM generalizes, the authors visualize the 2p times 2p matrix given by the square root of the AGOP of the final iteration of RFM, referred to as feature matrices. For RFM trained on modular addition, subtraction, the feature matrices exhibit a visually evident striped structure, suggesting a more precise characterization. The authors note that the feature matrix M at the final iteration of RFM on modular addition, subtraction is of the form M equals AC, CA, where A, C element of RP times P and C is an asymmetric circulant matrix. Furthermore, A is of the form C1I plus C211, for constants C1, C2. Similarly, RFM successfully learns multiplication and division. However, in contrast to addition and subtraction, the structure of feature matrices for these tasks, shown in Figure 3b, is not at all block-circulant. The authors demonstrate that reordering the rows and columns of feature matrices in modular arithmetic tasks reveals a hidden circulant structure. This reordering is achieved using group theory, specifically the cyclic group Z** operator P, where P is a prime number. The reordering procedure involves moving matrix entries based on their indices, using the discrete logarithm base G, which converts modular multiplication, division into modular addition, subtraction. To evaluate the progress of feature learning in modular arithmetic, the authors propose 2 measures: circulant deviation and AGOP alignment. Circulant deviation measures how far a feature matrix is from being block-circulant, which is a natural structure in modular arithmetic. It is defined as the total variance of the wrapped diagonals of a subblock of the feature matrix, normalized by the Frobenius norm. The authors show that circulant deviation exhibits gradual improvement during training with the RFM model and is close to 0 at the end of training, supporting the observation that the feature matrices contain circulant blocks. AGOP alignment is proposed as a more general progress measure applicable beyond modular arithmetic. AGOP alignment between 2 matrices A and B is defined as the standard cosine similarity between their vectorized forms, denoted as ρ, A, B. In the context of RFM or neural networks, AGOP alignment at iteration T is given by ρ, mount, M** operator, where mount is the AGOP at iteration T and M** operator is the final AGOP of the trained model. This measure of alignment exhibits gradual improvement in the regime where test loss is constant and large, similar to circulant deviation. Figure 4 demonstrates that random circulant features enable standard kernels to generalize on modular arithmetic tasks. Specifically, RFM with a Gaussian kernel on modular addition and multiplication for modulus p equals 61 is compared to a standard Gaussian kernel machine trained on random circulant features. The results show that standard kernel machines trained on feature matrices with random circulant blocks outperform kernel RFMs that learn such features through AGOP. The form of feature matrices given in observation 1 is key to enabling generalization in kernel machines trained to solve modular arithmetic tasks. By generating a random circulant matrix C and constructing the matrix M** operator with C1 equals 1 and C2 equals 1, P, It is demonstrated that transforming data with m*operator 1/4 enables standard kernel machines to learn modular arithmetic. Directly enforcing circulant structure in the submatrices of mount throughout RFM iterations accelerates grokking and improves test loss. These experiments provide strong evidence that the structure in observation 1 is key for generalization on modular arithmetic and, furthermore, no additional structure beyond a generic circulant is required. The AGOP alignment measure provides a more general progress metric, as it does not rely on assumptions about the structure of the AGOP. In the realm of neural networks, the concept of grokking has garnered significant attention, particularly in the context of modular arithmetic. Grokking refers to the phenomenon where a neural network gradually learns to generalize, often preceded by a period of memorization. A crucial factor contributing to grokking is the presence of block-circulant features, which facilitate the learning process. To quantify this phenomenon, researchers employ measures such as circulant deviation and AGOP alignment. These metrics provide insight into the gradual progress towards generalization, enabling the identification of neural networks that are more likely to generalize well. The authors extend this concept to two-layer neural networks, demonstrating that the grokking phenomenon is not unique to modular arithmetic. Through a series of experiments, they showcase a gradual learning process, dispelling the notion of a sharp transition towards generalization. The neural network architecture employed in this study consists of a two-layer network with a ReLU activation function in the hidden layer. The training process involves optimizing the network using stochastic gradient descent with a learning rate of 0.01. Experimental results reveal that the circulant deviation and AGOP alignment metrics effectively capture the gradual learning process, indicating a strong correlation between these measures and the network's ability to generalize. These findings have significant implications for the development of neural networks that can effectively generalize to unseen data. The authors investigate the feature matrices of neural networks trained on modular arithmetic tasks, specifically addition, subtraction, multiplication, and division modulo 61. They use quadratic activations and the ADAM-W optimizer. The feature matrices, referred to as neural feature matrices, NFMs, exhibit block-circulant structures, similar to those observed in random feature models, RFMs. The NFMs are defined as the matrix product WW, equivalent to the uncentered covariance of network weights. The authors reorder the NFMs for networks trained on multiplication and division with respect to a generator for Z to observe the block-circulant structure. The block-circulant structure is evident in both NFMs and RFMs, suggesting similar feature learning. A sharp transition in test loss during training is observed, consistent with prior work, and not an artifact of averaging the loss over all output coordinates. The test loss of individual correct output coordinates closely tracks the total loss, verifying this phenomenon. The emergence of block-circulant features is a key observation, related to the mechanism of feature learning in these models, as posited by the neural feature ansatz, NFA. The research on page 12 examines the utilization of random circulant features to enhance generalization in neural networks for modular arithmetic tasks. It compares the performance of networks trained on one-hot encoded modulo p integers with those trained on integers transformed using a random circulant matrix. The results indicate that networks trained on transformed integers achieve 100% test accuracy within several hundred epochs, whereas those trained on non-transformed integers do not reach 100% accuracy even within 3000 epochs. The study also explores the correlation between the square root of the AGOP and the NFM, finding a high correlation of greater than 0.92. Additionally, it discusses the use of circulant deviation and AGOP alignment as measures of progress, revealing gradual improvements in these metrics during the training process. The authors of the research paper delve into the impact of various regularization techniques on neural networks when training on modular arithmetic tasks. A comparative analysis is conducted between no regularization, weight decay, and AGOP regularization, revealing that AGOP regularization facilitates grokking, akin to weight decay, in instances where the absence of regularization leads to poor generalization. The paper also presents theoretical support for the notion that kernel machines equipped with circulant features learn generalizing solutions for modular arithmetic tasks. It is demonstrated that there exist block-circulant feature matrices such that kernel machines equipped with these features and trained on all available data for a given modulus solve modular arithmetic through the Fourier Multiplication Algorithm, FMA. The FMA is a three-step process. First, the discrete Fourier transform, DFT, is computed for each digit vector. Second, the elementwise product of the transformed vectors is computed. And third, the output class is generated through a complex inner product. This can be concisely written as equation 11. For specific inputs, such as x equals a circled plus eb, the second step simplifies to equation 12. Using the unitary property of the DFT matrix, the output of the FMA is shown to be equivalent to modular addition, as given by equation 13. The authors also provide a remark on the FMA, noting that their description uses all entries of the DFT, while prior works allow for utilizing a subset of frequencies. Furthermore, the FMA for subtraction is given by equation 14. The paper concludes with the statement of a theorem, which is not explicitly presented on this page. Theorem 5.1 reveals that a kernel predictor, trained via kernel ridgeless regression, can be equivalent to the Fourier multiplication algorithm for modular subtraction. This equivalence is achieved by employing quadratic kernels with circulant matrices. The proof of this theorem, detailed in the appendix, supports the use of block-circulant feature matrices in solving modular arithmetic tasks. The paper also delves into the connection between circulant matrices and the Fourier transform, as well as the relationship between neural networks and kernel methods in learning similar features for these tasks. In conclusion, the paper discusses recent developments in understanding generalization in machine learning. It highlights the limitations of using training loss and validation loss as predictors of test performance, and the importance of feature learning in determining emergence. The discussion on page 15 delves into the challenges of observing progress in learning modular arithmetic without access to a fully trained generalizable model. It highlights the need for a deep understanding of the algorithm implemented by such a model or access to it. The concept of posteriori progress indicators is introduced, which requires either a non-trivial understanding of the algorithm or access to a model like the circulant deviation or the inverse participation ratio. The importance of feature reordering is emphasized, using Fig. 8 as an example, to reveal hidden patterns. The section also explores the surprising nature of learning modular arithmetic, contrasting it with continuous ML settings. It touches on the concept of low-rank learning, matrix completion, and how neural networks can recover low-rank matrix structures. The idea that grokking modular operations can be viewed as a low-rank prediction problem is posited, with grokking, or the rapid emergence of skills, is often observed in neural networks, but its underlying mechanisms remain poorly understood. This research reveals that grokking can also occur in feature learning kernel machines, challenging the notion that it is specific to neural networks. The authors demonstrate that feature learning can happen independently of improvements in both training and test loss, contradicting existing generalization theory. The study highlights the role of AGOP BASED mechanisms in feature learning, which have been shown to account for various deep learning phenomena, including generalization with multi-index models, deep neural collapse, and low-rank matrix completion. Crucially, the explanation for grokking cannot rely on mechanisms specific to neural networks, as it has been observed in a kernel model with a linear feature learning mechanism. This means that explanations depending on weight magnitude or neural circuit efficiency are insufficient to account for the phenomena described. Instead, the authors propose that the RFM framework provides a more comprehensive understanding of grokking and its relationship with feature learning in kernel machines. The findings have significant implications for deep learning and generalization, challenging existing theories and reinforcing the narrative of rapid skill emergence in neural networks. The study demonstrates the practical and theoretical power of the RFM framework, providing new insights into the nature of grokking and its role in machine learning. It appears that the provided transcript is incomplete, as it only mentions, this page of the research paper discusses the acknowledgements and, without providing further content. Please provide the complete transcript, and I'll be happy to refine it according to the guidelines you specified. In the realm of machine learning, recent research has delved into several key areas, including implicit regularization, Jacobian regularization, and dimension reduction. These topics are crucial for understanding and enhancing the performance of machine learning models. Implicit regularization, a technique that aims to improve model generalization by adding a penalty term to the loss function, has been explored in various studies. For instance, one paper examines how different types of penalties can lead to distinct forms of regularization, affecting model performance differently. Another study investigates the role of early stopping as an implicit regularizer, demonstrating its effectiveness in certain scenarios. Jacobian regularization, which involves adding a penalty term based on the Jacobian matrix of the model's output with respect to its input, is another area of interest. Researchers have shown that this method can help reduce overfitting and improve model robustness. A notable paper discusses the use of Jacobian regularization in neural networks, highlighting its potential benefits and limitations. Dimension reduction techniques, such as principal component analysis, PCA, and TSNE, are essential for handling high-dimensional data in machine learning. These methods aim to preserve the most relevant information while reducing the dimensionality of the data. A recent study compares the effectiveness of different dimension reduction techniques on various datasets, providing insights into their strengths and weaknesses. These research papers collectively contribute to our understanding of machine learning models and their optimization. They highlight the importance of regularization techniques and dimension reduction methods in enhancing model performance and generalization capabilities. Radhakrishnan et al. Introduced linear recursive feature machines, a novel approach capable of provably recovering low-rank matrices. This contribution is significant, as it enables the development of more efficient and accurate machine learning models. In a separate study, Rogers and Laccioni analyzed key claims in large language model (LLM) research, revealing a long tail of footnotes that often go unaddressed. This finding highlights the importance of carefully evaluating the validity and reliability of LLM research claims. Sheffer et al. Investigated the phenomenon of emergent abilities in large language models, questioning whether these abilities are merely an illusion. Their research provides valuable insights into the limitations and potential biases of LLMs. Thilak et al. Conducted an empirical study on the slingshot mechanism, shedding light on its role in machine learning. Meanwhile, Trivedi et al. Proposed a consistent estimator of the expected gradient outer product, a crucial component in many machine learning algorithms. Trotman et al. Delved into the covariance structure of convolutional filters, offering a deeper understanding of their functionality. Varma et al. Explored the concept of grokking through circuit efficiency, providing new perspectives on the inner workings of neural networks. Wei et al. Examined the emergent abilities of large language models, while Yuan et al. Developed an efficient method for estimating the central mean subspace via smoothed gradient outer products. Zhang et al. Presented a mechanistic explanation of neural networks, and Zhu et al. Investigated catapults in stochastic gradient descent, (SGD), and their impact on generalization through feature learning. These studies collectively advance our understanding of machine learning and artificial intelligence, highlighting innovative approaches, addressing critical limitations, and exploring novel concepts. In fully connected neural networks with one hidden layer, the neural feature ansatz is restated, stating that the matrix product W1W1 is proportional to the gram matrix G, FNN, with a cosine similarity of plus or minus 1. This phenomenon holds for a matrix power alpha element of 0, 1, with alpha set to 1/2, consistent with previous results. The model and training details are outlined, including the use of a Gaussian kernel with bandwidth L equals 2.5, and one hidden layer neural networks with quadratic activation functions and no biases. The Atom W optimizer and mean squared error loss function are employed for training, conducted on a single A100 GPU with specific hyperparameters and initialization methods. A reordering procedure for feature matrices is introduced, based on group theory concepts. The multiplicative group ZP is leveraged, which is a cyclic group of order P1. A generator G element of ZP is utilized, representing the group as Gi, I element of 1, P1. This generator is used to reorder the features according to a map phi G, analogous to the discrete logarithm base G. The reordered feature matrices exhibit a specific structure, with circulant blocks, as shown in Figure 3c. This reordering procedure is applied to the bottom, P1, times P1, subblock of the feature matrix, excluding the first row and column which are 0. In the random feature model, RFM, enforcing circulant structure is crucial for solving modular arithmetic tasks efficiently. To achieve this, the authors propose a method to reorder the RFM matrix based on the smallest generator, ensuring that the choice of generator does not affect the observed circulant structure. This reordering enables the enforcement of circulant structure at every iteration, resulting in improved test loss and accelerated grokking on tasks such as addition. The paper also explores the capability of RFM to solve multiple tasks simultaneously. Specifically, the authors train RFM on two modular polynomial tasks with modulus p equals 61 and demonstrate that the model can grok different tasks at different training iterations. Notably, task 1 is solved before task 2, illustrating the model's ability to learn and adapt to various tasks. To further illustrate the effectiveness of RFM, the authors provide an example of fast modular arithmetic, FMA, for p equals 3, showcasing how FMA outputs the correct result for a given input. Additionally, they present supplementary results and proofs, including a lemma that states that a subblock of a matrix C is either circulant after reordering by any generator of Z** operator P or not circulant under reordering by any such generator. This lemma provides a theoretical foundation for the author's approach to enforcing circulant structure in RFM. Lemma G1 establishes that any circulant matrix C times, reordered by generator Q1 of Z** operator P, remains circulant when reordered by another generator Q2. This is proven by demonstrating that C is constant on the diagonals under Q2 reordering. Building on this result, lemma G2 diagonalizes circulant matrices U, expressing them as U equals FDF. Here, F denotes the discrete Fourier transform, DFT, matrix. F represents the elementwise complex conjugate of F, and D is a diagonal matrix with diagonal entries square root P foo, where U is the first row of U. The proof of Theorem 5.1 is then presented, which revolves around kernel predictors for modular subtraction and addition. This proof crucially demonstrates the equivalence of these kernel predictors to the Fourier multiplication algorithm, a fundamental result in this domain. The paper presents a novel method for solving modular arithmetic problems, particularly focusing on low-rank solutions for addition tasks. It introduces the concept of encoding and decoding maps, including the linear map phi that transforms vectors into complex numbers and its inverse psi for decoding. The method leverages the properties of circulant matrices and their diagonalization by the Fourier matrix to achieve low-rank solutions. The authors derive an expression for the function flat, x, that represents the output of the method, involving modular arithmetic and the use of the Fourier matrix. This approach offers a unique perspective on solving modular addition tasks with a lower rank compared to traditional methods. The construction of quantum Fourier transforms for modular arithmetic operations involves a series of complex mathematical transformations. The authors begin by defining a map psi from C to Rp, which sets all entries to 0 except for the largest one, and computes the inner product in C considered as R2. This map is then modified to be differentiable. A quadratic map M is introduced, performing complex multiplication on C2. The composition psi m phi implements modular addition, with phi being a linear map from Rp to C2. The authors demonstrate that the algebraic gate operations, AGOP, of this composition have a rank of 4. For multiplication, the authors reorder the non-zero coordinates by the discrete logarithm with base equal to a generator of the multiplicative group, while keeping the order of index 0. They modify phi to remove index A0 from the sum for inputs A. The decoding map psi is also modified to return 0 when z equals 0, and otherwise, it returns the maximum inner product of z with the basis vectors. The composition psi m phi with reordering implements modular multiplication modulo p, and the AGOP will also be of rank 4. This technical explanation highlights the key steps in the construction and the properties of the resulting quantum circuits. The alternating gradient optimization procedure, AGOP, is a crucial component in the evolution of random Fourier matrix, RFM, training. This process involves reordering the AGOP before and after optimization, as depicted in Appendix Figure 1. The reordering significantly improves the performance of the RFM. Furthermore, training a Gaussian kernel RFM on X plus Y mod 97, as shown in Appendix Figure 2, demonstrates the test loss and accuracy plotted versus RFM iterations. The performance of the same model is also evaluated by modifying the M matrix to have an exact block-circulant structure, as stated in Observation 1. This modification leads to enhanced performance, emphasizing the importance of the M matrix's structure in RFM models. These findings highlight the potential of RFM models in solving complex mathematical problems and the significance of optimizing the model's parameters, such as the M matrix, for better performance. The RFM iterations for two tasks, learning x2 plus y2 mod p and x plus y mod p, are discussed. Test loss and accuracy results demonstrate the RFM's performance. The RFM is trained using a Gaussian kernel on modular arithmetic tasks. Visualizations of the neural feature matrix, NFM, and the square root of the AGOP before and after reordering by the discrete logarithm are included, illustrating the impact of reordering on the neural network's features. In the context of modular addition tasks, the effects of regularization on the training dynamics of neural networks are investigated. A one-hidden-layer fully connected network with quadratic activations, trained on modular addition with p equals 61 using vanilla stochastic gradient descent, SGD, fails to achieve 100% test accuracy without regularization, as demonstrated in Appendix Figure 5. However, incorporating weight decay or AGOP regularization enables the model to reach 100% test accuracy and exhibit grokking behavior. The AGOP regularization term is defined as the trace of the AGOP, a measure of the alignment between the neural network's parameters and the underlying data distribution. AGOP regularization leads to better test accuracy and faster convergence compared to weight decay. In Appendix Figure 6, kernel RFMs are trained using the Mahalanobis Gaussian kernel for X plus Y mod 97, and the test accuracy, test loss, and AGOP alignment are plotted against the percentage of training data used. A sharp transition in test accuracy is observed with respect to the training fraction, whereas the test loss and AGOP alignment exhibit gradual changes. All models converge after 30 iterations, indicating a stable state. The results suggest that AGOP regularization can be an effective tool for improving test accuracy and convergence of neural networks, particularly in scenarios where the underlying data distribution is complex or has certain structural properties. These findings have implications for the design of neural network architectures and the development of regularization techniques that can adapt to different data distributions.